Hello everyone, this is part 2 of the Gaussian function. In the first video, we have seen the various parameters and how they affect the function. We had seen two functions. One was not normalized. In this video, we will be using the normalized function, which has two parameters, a as the center and sigma as the width. And we had also seen several examples in physics. So they can be broadly classified into two different categories. One is the usual thing where we use this as a function, continuous variable, which comes in heat and thermodynamics, modern physics, laser physics, to name a few. And on the other hand, there are some applications where this is used as a probability. The Gaussian function comes as a limiting function of the distribution. Such things appear in statistical mechanics, quantum mechanics, or error analysis. So in this video, we are exclusively looking at the integral of this function, integral between two integral lower limit a and upper limit b, what it means for probability and what it means for continuous function. For probability, it is straightforward. It is a probability between a and b, where the total probability is such that it is 1. Minus infinity to plus infinity is 1, and with any limit, it is going to be, any other limits, it's going to be less than 1. Whereas for continuous functions, this integral represents the amount of that physical quantity. For example, if you're talking of light, if this continuous function represents a light, then area under this graph would represent amount of energy present within certain frequency or wavelength limits. So before the starting, let's quickly summarize what we have seen. There are two parameters. Now a is the width and b is the center. So let's put b is equal to 0 and a is equal to 1, and let's generate the function. So this is how it looks. And if we change the parameter b, it stands for the center, that the center will be shifting. Or the parameter a, which controls the width. If I increase a, the width increases. If a is decreased, if a is decreased, so now that was a brush up. Now let us look at the area under this graph. For that, let us put this. So this slider over here will help us set the lower limit, and this slider over here will be used for setting the upper limit. So first, let us put it at the extremes. So we are dealing with a Gaussian function which is centered on 0 and width of 1. Now over here, the integral is taken between -5 and +5. And the value of integral is 1. So this is shaded here as the area. So this is the normalized function. So in probability particularly, what happens is the value between sigma, 2 sigma, or 3 sigma is taken. What do I mean? One of the famous things is, what is the 1 sigma value? Let me put lower limit at 1. So since the width is 1, so when I put it -1, it is 1 sigma to the left, and this is 1 sigma to the right. So this is the area under the curve. 1 sigma is 68.23% or 0.68. What about 2 sigma? 2 sigma is 95%. For example, in error analysis, we write plus minus sigma, that is 68%, or in some other applications where particularly machine learning, we use 2 sigma value, that is 95.45%. Within 3, sorry, this is within 3 sigma. So within 3 sigma, it is 99.7. 4 sigma, it is 99.99. And in the simulation, we can go all the way to 5 sigma. It's almost 1, although it displays 1. But as you know, this function extends from -infinity to +infinity. So it's practically, it is 1. It could be 99.69 or 79. And let us look at 0 to 1. Let's put left integral at 0, the lower integral. So this is the half, that is integral 0 to 5. This represents 50% of the area. Also we can see minus 5 to 0. This is 50%. So as you can see, this is a symmetric function. So this half covers 50% of the area and this half covers 50% of the area. Another interesting thing, we can look from minus infinity. For us, minus 5 is almost like a infinity, minus infinity. So if we increase the upper limit, let us see what happens. So up till 4, also there's not much of area, as you can see. So minus 5 to 1.4, minus 5.5 to 2.4. So another interesting visualization we see is, given a Gaussian function, given a function rather, how do we know it's a Gaussian or not? So for that, the area under the curve, it is known as error function, that is integral minus infinity to a certain limit, upper limit. And if the upper limit is seen as a parameter that keeps on changing, how does the graph look like? What do I mean? Let us, I'll put lower limit at minus 5, upper limit I change slowly, or upper limit I'll change it in steps. Minus 5 to minus 4, you can see there's a red dot appearing. So this is same number which is appearing here, area under the curve. I'm plotting as a graph. Only I'm dividing this number by 2 because my y-axis limit is set to 0.5, and I know that the maximum area under the curve will be 1. So 1 is not displayed here, hence this dot should be read as this number divided by 2. So given a distribution, if you want to know whether it is Gaussian or not, we can make such a plot and see if it is appearing like this or not. Now I have taken large steps. Next I'll take very small steps. You can see it is a S-shaped curve. This is known as error function. And for an ideal Gaussian function, this looks like a S-shaped, but whereas for real experimental data, there'll be little bit variations here, there. And this kind of a plot is also used in lasers, for example, uh, to find the beam width of a laser. The power is found out between one extreme and the other extreme is changed using a blade, and that results in this kind of a graph. And this S shape is related to the width of the original distribution. So this original distribution would change depending on the Gaussian function. So this is all for this second round of Gaussian function. Thank you.